So, good evening, everyone. Welcome to the final installment of Creative Tech Talks for the year 2020. Today's talk is on mastering distributed tracing. So, our presenters are Tharidu Thundenia and Pubudu Sitinamalwa. Tharidu, of course, better known as TT by all of us, is heading a team which handles systems engineering, big data analytics, distributed computing, site reliability engineering, and so on. He's interested in solving distributed computing problems. And Pubudu is one of TT's teammates. So he's also into SRE, machine learning, cloud computing, big data, and so on. And his interests are also in distributed computing and machine learning. So I now hand over to TT to start the session.
Okay. Okay, thank you, Kanchan. So today's talk is about distributed tracing, especially distributed tracing in the context of cloud-based microservices. So this is the agenda that we are going to cover today. So first of all, we'll try to get the background cleared about what's the new cloud computing landscape is about and how microservices behave in the new cloud-based microservices architecture, and try to find the problem of monitoring or observing microservice in the cloud. So we'll try to first establish that problem and try to see how distributed tracing would help us to overcome some of these obstacles of monitoring and having a good idea about a machine microservice in cloud. So that's so we are going to look at how distributed tracing would help us in that area and some of the basic concepts of distributed tracing. Then we'll look at some of the existing tools available in the industry. Some of them are open source and some of them might be commercial, but we'll still discuss the approaches that they have taken to solve the problem of observing microservices in the cloud. And later on, Pubudu will show you a live demonstration on how we can instrument a small application using a new distributed tracing framework called Open Telemetry, which is very new to the community, and most of the community is getting behind it and try to make it as the de facto standard for distributed computing in the cloud in the future. So we are trying to touch one of the latest additions to the open source community in the distributed tracing domain. So that's the overall agenda for us today. So I'll start with taking you through the current cloud infrastructure or the current cloud landscape if we take. So as you can see, there are a lot of boxes. So you don't need to go through all of them. I just wanted to put it out there to give you an idea about there are so many lot of technologies out there that are helping people to deploy applications into cloud, manage them in the cloud, and monitor them and observe them in the cloud. So this Cloud Native Foundation, Cloud Native Computing Foundation, CNCF we call it, started around 2015 to create a vendor-neutral home for most of these emerging open source technologies or open source projects to be in a single place, and they help these projects to be sort of interoperable, guide them to have best practices involved, implemented in their products and things like that. So the Cloud Native Foundation is kind of a place that you can go there and see, okay, what are the new things in each of these areas. Okay, if you take container orchestration management, or like databases in the cloud, what can I use these days? There will be a lot of guidelines, and you can see there are a lot of things happening. So our discussion today is focused on the rightmost box where it says the observability and monitoring, which is even entire community has identified as a key factor in cloud-based distributed computing or cloud-based microservices. Where okay, there are a lot of technologies that have come forward, allowing people to, when it comes to the CI/CD pipelines, the continuous integration and development pipelines where developers can seamlessly push new features, add new functionality to their applications very easily. But at the same time, the community has identified where, okay, at the same time, we need to have mechanisms to measure and monitor whether these applications are running as we expected, or like, are they performing the way that we are expecting. So to do that, there are a lot of technologies, there are a lot of technologies being built up for this monitoring and observing microservices space. So if you might have used some of them, there are things like Prometheus, Grafana, some of the most commonly used monitoring tools. But when it comes to microservices in cloud, there are certain new challenges that are coming in where we need to address using some additional mechanisms rather than the traditional monitoring solutions. Some of these traditional monitoring solutions might be lacking some new challenges that microservices bringing into the cloud. So we'll look at what are the important aspects that we have to monitor in a cloud when it comes to, especially when it comes to microservice, and some of the challenges that are involved in monitoring a microservice application in a cloud environment. So moving on. So before moving on to what microservices bringing into a cloud environment, or what challenges microservices bringing into a cloud environment, let's look at like what's observability, what's observable application in cloud means. So there's no clear definition anywhere in the internet or anywhere that has defined, okay, this is what observability is. So there are a lot of discussions, debates around what's observable microservice, or what's observable application in cloud. So this is something that I put up. So we can call a particular application or a system in cloud as observable if that application or the system, if you can answer the questions that are coming about your solution precisely and with confidence. For example, if you can answer anything that people ask about your system with confidence and accuracy, if you have features to answer that answer questions on your system, then we can call it as an observable platform or observable software in the cloud. So what are the typical questions that people might ask? So if you look at some of the questions that people ask, okay, you have a microservice in cloud. If you click next, Bogdu, we might have some questions I put up. Okay. So for example, people might come in and ask, okay, let's say you have application deployed in the cloud, which is a microservice, and it consists of like few microservices serving certain endpoints. So people might suddenly come in and ask, okay, our services are slow today. So how do you start? Okay, where do you look at and see, okay, what is slow, where it is slow, whether all the customers are facing this problem, or if this specific person is facing this particular problem. So basically troubleshooting, actually there might be a problem, so troubleshooting a misbehaving application in cloud. Do you have all it takes to troubleshoot a situation like that? Okay, going further than that. So we know that with the invent of these CI/CD pipelines, Kubernetes, containerizations, developers can seamlessly push new code into your application. It could be any time of the day that anyone can, if they can pass a test and deploy something, most probably they'll be deploying something into the production. So let's say if there was a new deployment happened 5 minutes ago, are you confident that all the latencies and error rates have not been affected at any means by this new deployment? Can you confidently say that? Or if you might be expecting a performance improvement by deploying something. Can you verify and see, okay, whether the intended improvement happened in the production system after this deployment? So do you have what it takes to measure that and quantify that? Going further, your product owner or a higher management might ask, come in and ask, okay, we need to improve our performance in this system. Okay, this application is performing, okay, it's been going on for like 5 years. We need to improve its performance. So where do you start? What to improve? What's slow at the moment in your application? Like you might be having, if it is a microservice ecosystem, you might be running like 5 to 10 to maybe hundreds of services in the cloud at the moment, owned by you or owned by your teams. So where to start? What's slow? What has been giving the customers most problems? So do you have a profile like that? Have you profiled them? Do you have a repository or a set of measurements that you have been doing over a period of time where it will reveal you, okay, how my application behaved over the time? What are the slow points, or what are the things that are lagging in my project? So even going further than that, let's say you want to add a tiny bit of new code into your application, or let's say you have a particular service that has been doing like 5 dB calls and retrieving some values and doing something. You just, for a new feature, you just think, okay, I need to add one more database call to this function or this application. So can you imagine what kind of overhead it would cost into your system? Okay, can you measure how much of a overhead from latency side it will induce to the existing application? So most probably you might do a guesstimate, like, okay, usually 5 database calls would take this function to return in like 500 milliseconds, then it will take 600 milliseconds. But can you definitively say that? Can you precisely measure what's the new overhead that my function goes to my application? So to answer things like that, things like what I have just mentioned, and there could be many other questions, like, in a microservice setup, there could be like tens of hundreds of, maybe even thousands of services that a particular request might go through. So without going any further, at least if you know that for a given request, what are the dependent services that it goes through, like simply by looking at, is there any place that you can look at and see, okay, this request is there. If you are not the developer, or if you are not the co-developer of that product, if you are an outside person, do you know, okay, this request, where does it go through in my system to give a response? Things like that. We can categorize those questions or the observability traits as like monitoring performance in your system. Then, as I said, profiling workloads, how each component or the function behave, or what kind of latencies that they are taking, what's the usual error rates that they are giving out. Plus, most importantly, quickly scoping and troubleshooting performance issues. If someone says, okay, your system might not be healthy, do you know where to look at, like without going to like 100 services and checking their logs? Do you know how to pinpoint where could be the problem is? And later on, maybe even debugging production issues or bugs. You might need observability into your ecosystem. So having said that, what would help us to bring in these insights into application? Usually, the traditional approach is to use logs, as we all know, and plus, until recently, people have heavily used metrics, like the metric systems like Prometheus helps you to define metrics in your code, like via counters, histograms, to publish metrics about the application, about how long does this function to code, does this particular method took to contribute. But in a distributed setting, in a cloud-based setting, where in a cloud-based settings, when you especially have microservices where each request would go through multiple services and crossing multiple boundaries to return a service, you cannot rely on logs and metrics only. There has to be something else. Then people have realized, okay, we might need to have a mechanism where it can track the propagation of a request through these different distributed components, and have a holistic view about a particular request, or an entire view about how it behaved throughout these microservices in the cloud. So, so that's why tracing becomes important, especially in these distributed settings. So we'll next let's look at, like, so we call these three things as the three pillars of observability. It's being discussed widely in the industry. None of these things alone will help you to, like, having only tracing will not help you to have full observability into your microservices in cloud. Having logs only will not help. So combination of these things engineered in a smart way will definitely help you to answer the questions that anyone would ask you about your system. Yeah. Then moving on to the next slide. Yeah, moving on to the next slide. Let's look at, like, what kind of challenges that microservices will bring into your cloud-based environment. What makes it harder for you to monitor a cloud-based microservices setup. If I just say, okay, observing cloud-based microservices is hard, if you agree, I can move forward, but it's better to stay here and like discuss this problem space a little more. Then we can see how we can solve these problems going forward. Yeah, the diagram that we have shown here is the one that Microsoft has provided as the reference architecture for deploying microservices in cloud. So it need not to be the exact same components, but typically if you take a microservices deployment in cloud, you would have at least one of these things, or most of these components involved. This is what Microsoft recommends for their cloud. So if you take Google or Azure or Google or AWS, most probably you might be using the complementary technologies in their stacks for this. So if you look at this, as you can see, we have these Azure load balancers. Then we have the egress proxies that usually load balance, rate limit, and route services to different microservices that we are running. Then we have the backend microservices that we run. In turn, these microservices will communicate with each other, plus some of these microservices might contact some external data sources like databases, or even make calls to the internet and do some work for you, and ultimately returning results. Apart from that, we have this CI/CD pipeline where allowing people to seamlessly deploy things into the cloud. So what's the new challenge that this brings in? Mainly the number of boxes that might involve in deploying a particular application. Previously, in old days, if you take, it's quite straight. Your entire code base, which consists of your business logic, would be running in a single node. So anything happens, it happens within that node. You can check the logs, check the machine's CPU memory utilizations, but now to serve a particular request, it has to depend on multiple components in the cloud. So basically what we have distributed in distributed environment is, even though we have distributed the problems as well. Previously, it was a single place that could have caused you a problem. If it is a monolith application, most probably the entire business logic might be running in a single place, even though it's clustered or something. But now, in order to succeed a single request, single particular API call, you might need to depend on like 10, 20 containers. So all these containers should be up and running, and the dependent databases should be up and running to serve a single request. So think about the things that can go wrong in a situation like this. So if something is going wrong, we have to quickly identify what's wrong. So as you can see, these things are independent software, like egress. If you take, it's Nginx, so it's an independent software. So if you deploy your own microservice containers, they are independent containers. So to troubleshoot that without any tracing mechanisms, just through logs, you have to go through to these each and every component and check the logs, maybe to troubleshoot something, which is virtually impossible, right? Even going further, if you take a single service or a single microservice, you can see it depends on few other microservices where it will be making RPC calls to two different services and waiting for a response and doing something. So inherently, cloud-based in a cloud-based environment, things are distributed. That distribution, when it comes to especially comes to microservices, introduce the factor of distribution in cloud introduces a lot of problems when it comes to observability. You have to find alternative ways. The traditional monitoring systems will not allow you to monitor a complete request in a cloud environment. That's guaranteed. So we have to find solutions. We have to find a solution how we can overcome that. So apart from the distribution factor, there's another thing that's come into the play or come into the mix where it makes it hard for us to measure microservices in cloud. It's the fact of concurrency, how concurrent execution of request evolved over the years. So if you take the old days, where you might be running a particular server, where it might be, even though there are child processes that this server works on, what would normally happen is your server will fork a child process, ask it to do something for you, and it will return something. Then you will ask for another child process maybe. If you take a particular request, that entire particular request executed in a single machine, maybe the child's executed in sequential fashion where it completes their workload. That's the no concurrency world where we lived in when we started our careers. So then came the multi-threading with basic concurrency models, where when we have the advancements of the CPUs, we were able to run multiple threads, but still all those threads were kind of sequential. If let's say if there's a particular request, that request might be completed by multiple threads, but sequentially one after another. Then you can run multiple threads like that in a system. So that's again not a hard problem to monitor since it's running on a single machine or even running on multiple machines. If you can induce the thread ID to the log, maybe since it's a single machine, you can concatenate the logs and see, okay, how a particular request behaved in the system. Then comes the cloud-based ecosystems, where it introduces a whole lot of new program paradigms, where to start off with things like actor-based systems, we call it, there's a popular framework called ACA, where it introduces this actor-based programming paradigm, where actor would, it's not object-oriented, so actor would receive messages and send out messages. Let's say a parent actor would send something to one of his childs. It doesn't know anything what happens after that. It just sends it out. It doesn't know even it got completed or not. So we call it the asynchronous concurrency, where the actor-based actor systems, the promises and futures that were introduced, and even the node-based systems, where even though it runs on a single thread, the threads has to wait until they get completed. If you take particular request in this asynchronous concurrency setup, a request might be started on a particular thread. It might be handled by a different thread in the middle, and the response might be sent to the client by a third thread. So if you can see, if you take a particular request, it has been handled by 3 different threads at least. It can be handled by at least 3 different threads within that process. So basically, if you take a particular thread, it might be handling multiple requests. It's not bind to a particular request. It might be handling multiple requests. It might finish off job of one request and hand over the work to another thread and serve something else. So this asynchronous concurrency models introduces a huge problem. How do you monitor a setup like that? So if you take a thread, it will be handling hundreds of thousands of requests. If you take a particular request, it might be going through multiple threads. Then comes the microservices setup. It introduces a whole new challenge, where it introduces another concurrency model called distributed concurrency, where not only for a particular request, the request might transfer through threads within a process, but it can jump through processes. As you can see, it can jump through 3 processes in this the rightmost distributed concurrency model. Plus, it can come back to a particular process and return the result. So think of monitoring a setup like this for a particular request. So it's quite hard, but that's the problem that distributed tracing would help to solve. So we need a way to trace or track the entire path of a particular request, how it travels through the different distributed components in a cloud. It could be the egress, the particular service A to service B, then coming back to service B and returning a result. So we need a way to stitch whatever happens in each of every process and have a complete view of the request generated somehow. That's what distributed tracing helps you to find. So I found, so when I'm reading material in the internet, I found this interesting quote. Most of the people have quoted, where so we replace the monolithic applications with microservices, so that every outage or every troubleshooting effort is kind of a murder mystery investigation. So it's actually like that. If you don't have the correct tools or correct setup, the correct observability aspects configured in your system, it will be like a murder mystery when someone says, okay, my latency is high, so you don't know where to look, you don't know where it is coming from. Yeah. That's the problem of distributed tracing. That's the problem that distributed tracing will help us to solve. It will not. So as we move on, we can see it's not a silver bullet, but it will help you to address most of these problems and give you a better ground to stay and be confident on your system. So yeah. So now let's look at what distributed tracing is and some of the concepts that are around distributed tracing. So if it, as we discussed, we need a way to traverse through a request as it travels through these distributed components. For example, let's say it is coming through a client, going through a load balancer, serving through an authentication server, then going through 2 different services. So we need a way to identify the workloads that has happened within each and every service, and how long they took, whether they got successful or not. And we need to have a way to publish those information for someone else to measure. So we call it a span, where it identifies a unique piece of work that's happening within a request. So we can go through these concepts in detail and how we implement them in practice. So I'll just set up the ground to discuss these points here. So we need something called span, which is a unique piece of work that's happening within a request. So we have, if you take an entire request, it will be having multiple spans, where spans represents work that has happened within a particular process. So you might have multiple spans happening on auth service and the initial services, and every component might be publishing spans. So then what we need, so we know, so these spans must be related to a particular request. We need a way to stitch these spans together and create a what we call a trace, which is related to a particular request. So we need a mechanism to stitch these spans. For that, what we need is each request, when it is calling something else, or calling a child process, or calling something after I have completed my work, what it does is it transfers something called the span context. Okay, I am this, I have done these things, this is the unique ID of this particular request, and you take on the work after this. So that guy takes the span context and it appends anything that might be unique for it, maybe sending it out further down the line. So at least if you have one unique ID that can be traversed through these distributed components, by that particular unique ID, you can stitch these things together and create create what we call the aggregated set of spans. What we call is a trace. So apart from traces, when you are publishing a span, you can add additional information that can be used later on for further analysis. For example, if it is a, let's say, a load balancer, it can add additional attribute like, okay, the source IP, or let's say the region that the request came in. The advantage is later on, if you have something like that from the load balancer span, later on you can altogether aggregate and see how many requests came in from different geographical locations, or it could be the client ID or the username. You can think of what would be helpful for you to troubleshoot and analyze and get an idea about your system and design the attribute structure that you want in a distributed tracing setup. So having said that, so it's not an easy task just to create spans. Okay, the concept is that you need spans, you need a context to be propagated, you need to collect, you need to have a traces collected, and you need to analyze them. But to do that, since this is not business logic, this is something else that we do for observability. With the new distributed tracing architectures, what we need to do is first we need to induce these spans into our code. We call it the instrumentation. So there could be instrumentation library that you select. Later on we discuss how we do that, but you need to select the instrumentation library and instrument your code to publish spans or publish telemetry about your system into some app. Then it's not the business logic. So someone else outside needs to collect them and send them to analyze. And you need a mechanism. So individual span would not mean anything for you. You have to stitch them together. But even having one trace about a particular request will not help you at any case. You need to collect these traces for all the requests that came into your system over a period of time. Or maybe you need to collect all the requests that came in to your system and do certain analytics. So next what we need to do is instrument, collect, and analyze these things. But while doing that, we have to consider some other factors. Scalability. So these modern cloud-based architectures, if you take a Kubernetes setup, they are designed to do auto scaling. If the number of requests that are coming into your system increases by 10 times, maybe you can have a pod autoscaler set up for your application where it will scale up by 10 times. Then the tracing ecosystem that's running underneath must be scalable in that case as well. Then the cardinality. So if the service is receiving thousands of requests per second, if you have added a new attribute called user email, so the cardinality increases. The number of unique users that are in your system will induce a lot of cardinality overhead for your system as well. You have to have the checks and balance whether what are the useful information or attributes that I'm going to introduce to the instrumentations in my distributed setting. Then comes the problem of storage. So think of a setup like Netflix or Uber or Amazon. Can they store all the requests that are coming in, or even though you have a mechanism to collect the spans and stick the traces, and can you store all the traces in one place? There will be a cost comparison. So this is not business logic again. So this is something that helps you to improve, helps you to identify what's happening, and this enables you to have a feeling about your system. But since this is not business logic, storing every trace that is coming into your system, storing every request that is coming into your system will not be feasible, because that infrastructure might cost you more than the application logic infrastructure at the end. So you have to find some checks and balances. What I am going to store, whether I'm going to create some summaries before I'm storing it. So those things you have to consider before storing them. Moving on, yeah. Then we'll see some of the approaches that people have taken to solve these distributed tracing problems. So usually there are few things that that has happened within organizations. If you take the predecessors of distributed tracing, Google has, as we know, they have a lot of distributed computing solutions. They have a lot of components running very in a distributed way. They have adapted a tool called Dapper, where they have published a paper with the techniques that they have followed to implement a distributed tracing mechanism within Google. So that has become the influential paper which has given rise to most of these modern distributed tracing tools. So they have successfully done that. They have successfully profiled the requests when they traverse through different components in a distributed setting. So they have given us some guidelines when it comes to designing and implementing a distributed tracing infrastructure along with your microservices in cloud. For example, you have to be concerned on these factors. For example, if you move forward, so the distributed tracing infrastructure has to be low overhead, where since it's not business logic, you cannot induce a huge computational overhead to collect traces, analyze them, and display them. Then if it is causing huge overhead to your business logic, then like if the applications are taking too long to publish the spans, create the spans, if you like, you should not give any overhead to your business applications. It should be very minimal. So you have to consider that as a key factor when doing instrumentation, planning, distributed tracing. We can do all that. There are ways that you can overcome this, just that you need to be aware of these factors. Then you need to have the application level transparency, where the underlying distributed tracing infrastructure, or the way the traces are happening, whether the collectors can't collect the traces or not, that shouldn't be transparent, that shouldn't be visible to any of the application logic that's running. So application should be able to continue with their own work, whether the tracing system worked or not, or whether we can collect traces or not. So that has to be carefully planned and designed, where what happens whether the tracing system works or not, application cannot be interrupted, but still all the traces we should be able to collect the traces. Then comes the scalability problem we discussed a little earlier. Then there's another important fact. Since we talked about real-time monitoring, troubleshooting, debugging applications, you need to have this tracing system available at all times, where whenever you want to troubleshoot something, whenever you want to debug something, the tracing system should be available at all times. Then comes the sampling problem, or the sampling concern that we have to consider. As I said, we cannot store every request in a tracing system. You have to think of a smart sampling algorithm, where we take the averages from each request and keep a sample of the request that would represent the whatever the things that are happening in my production system. The things that I keep would give you a realistic view about the actual system, but it's not the entire set of requests. Having entire set of requests stored is not practical, especially for a high volume environment. But if you're having a low volume traffic generating microservices setup, it could be feasible. But in a high volume setup, you have to think of a sampling mechanism. So distributed tracing systems consider that as a main concern as well. Yeah, going forward, then we can see if you want to implement a distributed tracing setup by hearing my talk, for example, where do you start and how do you start? What are the options that are available? So so there are a few open source. So there are few options actually. There are open source tools. You can select enterprise tracing solutions. You can pay some money and get this entire problem solved for you, which is expensive. Or even you can build your own distributed tracing technology, considering that the technology is the papers referring to these things. But that's again will be quite expensive. So if you look at the open source set of tools that are available, they have a lot of things that has happened in the past. We call open tracing, open sensors, Jaeger, Zipkin. Those things were there in the industry for a long time. Now, all these guys have come together and decided that without competing with each other, why don't we have a common standard, which is vendor agnostic, where whoever the person is giving you a backend to analyze it, we should have a common standard to instrument the applications. Otherwise, if you want to move from Jaeger tracing to open tracing, you have to re-instrument your entire code base. That's not going to work because some people might see some advantages in one project and things like that. Since all these are open source, people have come together and decided the open telemetry one with the telescope is the next generation open tracing toolkit that they will be focusing. All these companies have come together now and focusing on open telemetry, but open telemetry will be backward compatible as well. So we'll be going through open telemetry in quite detail. Also, there are a lot of commercial tools available. So you can choose one of them, which will have all these features that we have discussed. I have extensive experience with Lightstep, where we have working with it even at the moment. So they have quite cool features. Lightstep is founded by people that came out from Google, where actually the initial publishers of the Dapper paper are in Lightstep. So they know what they are doing. So likewise, we have few other distributed tracing tools that are out there, which is more or less doing the same theoretical side that we discussed, collecting spans, allowing the span context to be propagated, collect them, and allowing you to analyze them later on. If you go, another point to mention here is every big e-commerce company, or if you take Facebook, Yahoo, Uber, Netflix, you name it, everyone has their own, at least they are using something like this open sources thing, so have their own open tracing solution. That's 100% guaranteed and sure. Zipkin is originated from Twitter. As you know, open telemetry and open sensors originated from Google. Jaeger originated from Amazon. Jaeger originated from Uber. So even those who haven't open sourced their product might have their own distributed tracing solution built in, a custom solution built in for them. So if you're thinking of going into microservices in cloud in a fully fledged manner, you have to think of a distributed tracing solution. Otherwise, there are certain problems that you cannot solve in a setting like that. So going forward, even though we discussed, or I sold you the idea of distributed tracing, you might think it solves all the problems in distributed tracing and in distributed environments. It does not. It's not a silver bullet. Still, there are a lot of challenges that we have to overcome. But distributed tracing has been proving its value, and a lot of people have used it and make it useful for them, for their organizations. It has proven its value. Definitely, it's a great technology, or great set of standard that you can use. But let's just look at quickly some of the drawbacks that it brings. For example, some of the problems that you can see. Once, as we mentioned, the entire code base has to be instrumented. So once you instrumented, you cannot go back. Once you instrumented, it will be working forever. If you want to take it off, you have to take it off from your code. Otherwise, there are no on and off switches. So that's one problem. Then, at least you like it or not, there will be some computational overheads because it's not the business logic. This is something additional that you introduce to publish traces and do things like that. The other thing is you cannot instrument everything. So if you instrument everything, it will be a big mess, because every code might have to have some instrumentation for tracing. But let's say if you don't have some instrumentation for a particular code and you have to debug a particular issue, and you see, okay, if I had a span here, I could have easily identified what's going on here for clients. Then you have to do a re-instrumentation. That's another drawback. Then the sampling trade-off, as we said, we cannot store all the things, but if we have a stored trace, which means we have everything that's happened for that particular request. But if you don't have that particular request traced and stored, you don't know nothing but just an idea about what might have happened for it. So that's another drawback of this setup. But the concepts that I have explained, tracing, the context propagation, collecting, and analyzing, some people have taken some alternative approaches. That just for the completeness, I'm mentioning them. So if you want to do further reading, you can do further reading and see. There's a new set of way of doing that called pivot tracing, and there's another research paper called Pythia where they are introducing a dynamic tracing mechanisms where you don't have to instrument your application or instrument your setup. It just sits in your containers and extract values when they're making system calls, and identify the functions that are making the system calls and collecting those information together in the distributed settings. The earliest people who did this was called dtrace in the early MIT days when we used to do that, but that's not distributed cloud computing. It's a server-based setup where you can easily write a distributed dtrace script and without instrumenting anything on your application, collect whatever happens from your application with the system. But that's not helping in a cloud-based setup, but people have started trying that using this pivot tracing and Pythia setups. So that's it about the theoretical side, or the concepts behind distributed tracing. So Pubudu will take you through as the next steps of like showing you actual instrumentation using OpenTelemetry, giving you an idea about what OpenTelemetry is. So he has done a great job with a small demonstration. Also, he's been using these things daily in our applications that we are working at the moment in our client. Yeah, so with that, I'll hand over to Pubudu to take over. So after, if you're not bored after all this, we'll be able to answer some questions if you have. So I'll let Pubudu to continue.
Thank you, Titi, and hi everyone. So I'll be demonstrating you that a small application that I have instrumented with OpenTelemetry. And firstly, I will be giving a brief understanding of OpenTelemetry first. So what is this telemetry? Telemetry means it's a remote measurement. This word comes from two Greek words, tele and metron, which means remote measure. So basically, this is measuring remote systems on premises and getting these remote measurements to transmitted to a monitoring system and getting the overall picture. This is called telemetry in general. So to OpenTelemetry, as TT mentioned, this project is created by merging Open Tracing and Open Sensors to very popular distributed tracing projects. So basically, what OpenTelemetry provides is a set of softwares and tools that allows you to instrument and generate telemetry data and capture them. So with OpenTelemetry, you can cover all your organization's applications to get a very good understanding of the underlying functionality, how it went and what went wrong. So what makes this different? So as TT mentioned earlier, this OpenTelemetry library, the framework gives you a vendor agnostic implementation. So it also has a backward compatibility. So if you want to go with OpenTelemetry, you don't have to re-instrument all the code. You already have instrumented with Open Tracing, Open Sensors, Jaeger, or Zipkin. You can use OpenTelemetry with these existing instrumentations. So I will explain a few concepts in OpenTelemetry. First of all, it has a API specification, which explains how this tracing should be done, like how span should be defined and how the context should be propagated likewise. And then there is a SDKs actually for a lot of languages, which is the implementation of the API specification. And then there are agents and collectors, which collects these telemetry data that are generated through instrumentation live, and then exporters. Exporters help you to, the open telemetry is a tracing framework. It's not a visualization platform. So it allows you to add the instrumentation to get the details about the underlying performance and everything, but it does not provide a visualization layer. So you can use these exporters to connect this telemetry data that you have generated to an external visualization platform through exporters. And it also provides auto instrumentation for some frameworks, for example, like Kafka and Spring Boot. So there is a huge list of frameworks that OpenTelemetry supports auto instrumentation. You can find it in their website if you are interested. So I'll be explaining this a bit more. So this is the architectural overview of OpenTelemetry. It mainly consists with three parts. First one is the OpenTelemetry API, which has a trace API, which is responsible for creating and generating spans, and the context API, which is responsible for handling the context of spans, and the meter API, which is responsible for managing the measurements that are done in the code. And then there is semantic conventions, which are basically recommendations from OpenTelemetry on how to name spans, how you should use attributes, so on. So they also recommend a set of common attributes that you should be instrumenting for, like for a HTTP call. You should be adding the status code and status message kind of things. And then comes the SDK. It has a tracer pipeline, which is responsible for capturing the generated spans and export. And then the shared context, which is responsible for propagating the span context from one system to another. And the meter pipeline, which is responsible for aggregation of measurements that are done in the instrumentation. So the span attributes and measurements are a bit different. Spans provide you the overall picture of what's happened, and with the measurements you can, for example, get the CPU usage or disk usage at a time with respect to time, likewise. And then comes the collectors, and then exporters. The exporters, as I mentioned earlier, this is to export the collected telemetry data to a vendor, which would be a analytic platform or the visualization platform. And then these are the basic concept in OpenTelemetry. So this is these boxes A, B, C, D, E represent a set of spans. These could be a set of functions that are plotted against time. So as you can see, the function A has taken the longest time to complete. Likewise, it shows you a respective time span over the functionality over the trace. So trace is the collection of these spans. So through a trace, you can see the complete request flow. And then comes the context propagation. So instrumenting with OpenTelemetry can be done to a non-distributed system as well. So you don't need the context propagation. You can just instrument it with the spans and see how your application is performing. So what makes it distributed tracing is the context propagation. So context propagation allows you to propagate the span context throughout the system boundaries. So it can propagate the context from one system to another system over the wire. So they have specifications. They have specification to how to propagate this span context. So OpenTelemetry uses HTTP headers as the span to propagate the span context as HTTP header. So there are three main protocols you can see as trace context, HTTP propagator, correlation context, HTTP propagation, and B3 Zipkin HTTP propagator. So these you can choose any of these methods to propagate your span context. And also this is like serialization in Java. It make the span context, convert span context to a text format, and again it helps to build the span context from this header back in the another service to continue the tracing of this request. So there are two parts in this span context. One is the span context, which hold the context of the span, like trace ID, span ID, flags, and state. And there is also correlation context, which holds the data that we have added, maybe through matrix, and it helps to do the correlation analysis and filter kind of operations. So this correlation context is optional. So if you want to do more analysis, you can have those data integrated. Moving forward, this is the basic functional overview. If you implement this in a microservice architecture, so you will have the application code instrumented with OpenTelemetry, and it's connected to a collector. And again, in microservices, you will have a layer 7 proxy, which would be like Ambassador or Envoy, and databases. So there are some proxies like Envoy, which provides instrumentation. It's already been instrumented with open tracing, so it's very easy to get the whole picture from the request coming to a system to leave until it leaves to trace that. It's very easy with open telemetry. So, and at last it will be exported to a analytic backend like Elastic APM, Elastic Jaeger, Zipkin, or Prometheus. And they have also mentioned a set of instrumentation best practices. So one key thing they have mentioned is that when we are instrumenting, we should be most probably focused on an SLO, which means that we are measuring the customer's impact directly from this instrumentation. So these are the set of guidelines to use attributes that can explain the performance variations. So, and use semantic and descriptive attributes name. This is when a lot of teams are working together. So it's to like prevent that two teams are naming two different things as same name with the attributes. So it should be semantic. And also they recommend that we should use a shared library for attributes because there will be a set of default attributes that you can choose from to instrument your code. And when using attributes and logs events, it helps you to find the issues fast. And when choosing attributes, as TT mentioned earlier, we have to think of cardinality. So for example, if you have two attributes that have 5 different unique values, that would be cardinality would be 25. And if you want to add one more attribute with just 2 unique values, the cardinality will go up to 50. So you have to be very careful on this, and also be focused on SLOs and SLIs when instrumenting. So this is a sample trace that I have generated with my application. So it has two services. Service A, when it gets a request, it calls service B and do some work and do a database call, and then continue with doing a few other functions. So let's think that the developer has forgot to instrument function B. So it will have a trace like this. So if something goes wrong or something cause this function B to take very long time, we don't know what happened there, how long it took. So it's very important that, as TT mentioned earlier, to instrument what you need. And last, observability. This is not something we can like just buy, go to shop and just buy. So you have to engineer it from scratch. These are two open tracing analytic platforms, Zipkin and Jaeger. These are the UIs, as you can see. So I will be demonstrating on this in a second. So let's jump. Give me 2 seconds.
By Kudu is preparing for it, just remember, open telemetry will give you all the things that it requires for you to instrument, collect the matrices. So you have to choose your own analytics backend, which is Zipkin or Jaeger, that like we mentioned, or anything that you can pay and get. So which means the open telemetry infrastructure will collect the traces and push them to analytic backend. Yeah. So these two are purely open source platforms, so they might lack some features that the commercial products have. So we might be able to show you Lightstep as a commercial product. You will immediately see the additional features that they have.
Yeah, so this is Zipkin, and I have two backends, Zipkin and Jaeger. So at the moment, there are no traces in this exported to Zipkin or Jaeger. So I have created two demo applications, which acts like a client and a server. So this will be talking to each other, two different services. So just to demonstrate that the span is going over the boundaries. And yeah. So I'll be just explaining the code a little bit, just to have a peek on it. So now I am generating these spans as I have instrumented it. So it will be generating these spans continuously. So if we look into one trace in Zipkin, you can see I have these two services, and I have added a set of attributes to each and every span, and you can observe it by clicking each and every span. There are a set of attributes,
and you can see how long did every sub function took. Like for example, service B get function took 253 milliseconds. The other function took so the entire request took 6 seconds. But out of that 6 seconds, how did each and every part contributed for that latency? Like let's say so if you have 100,000 or like 2 days worth of traces, and someone is complaining, you can definitely quickly see by taking the traces into a different graph and see, okay, who's been taking long, okay, what function is being lagging. It could be the database, or it could be something else. Yeah.
So and also you can like compare it to see what function has taken the longest time, and also it provides you with the status pages, status code for the span, and also you can add a lot of attributes to identify the problems. Also you can add links and events to these spans. So if we look at Jaeger, now I will have I have two services. So as you can see, I will choose A and go to a span. So this is a different UI. So you can see how my functions went, how long it took, and what their attributes are.
Yeah,
Likewise.
even though you selected the service A, it shows that since it has a dependency between B, a particular request has to go through all these parts between different services. So that's a key advantage. So when you select it from one end, it knows where it came and where it went. So without going to individual services. Yeah.
And just to give a little bit of peek into the code. So this is how I have instrumented the with hotel. I don't know if you can see it properly. First of all, we have to create a span exporter, span processor, and get these traces connected to each other. Then you can define a span like this and give a proper name for the span, and you can set attributes like this for your span and process it. And also you can forward your span to a child process. Let's say I have forwarded to here, and there are set of functions that I have just added a dummy code just to induce latency for the function. So you can use this span as a parent span and create a child span for that. So that's what's being shown here. It's these are the child spans. So if I forward this, everything will get forward. This is the child span. Likewise, you can add attributes to your child spans as well to get more insights to this. So we have only added spans and traces. We are focused on traces basically, and you can also have matrices which provides you with counters and observers for measurements.
Yeah, just to stay on that, one thing is OpenTelemetry promises to be a complete observability platform where it will support tracing, logs, and matrices. But right now they are just supporting matrices and traces. In the future, they will support logs as well. So you don't need to switch between like different instrumentation for matrix, like Prometheus instrumentation for matrix. You don't have to go through like 3 different solutions to obtain observability. You can do the tracing, matrix, and logs instrumentations through a single library like OpenTelemetry in the future. That's what they're promising, and I think it's good if they can achieve that.
Yes. And we have also been exporting these data to Lightstep. You can see it here. So I've been exporting this data to Lightstep. They provide a public satellite that you can use, simply instrument and upload your data and see. So Lightstep provides cool features. So if you go to the Explorer, we can see how this request latency has been behaving. So as you can see, the 95th percentile of this request were around like 5 to 6 seconds. And
if you want to troubleshoot, it's like if someone is complaining my latency is high, you know that the ones beyond the 90th percentile might be causing problems. Then you select those things. Then you can see the correlations. Okay, if you have enough attributes, it will say the ones that are over 6 seconds mostly related to a service call like this or a database call, something like that.
And also they provide these filters and group by functions. So if you like filter it with this particular operation, it will give you stats.
Yeah, and you can go to a particular trace and show that how it behaves differently with.
So if I go to this this filtering, it shows this operation has 162 span counts and no errors. Likewise, so if we group by all the functions, it provides us with these stats, so it's easier to get more insights. So if I go to a particular trace, so this is how the trace looks like. it's kind of the same as the Zipkin. You can see the difference time it took for each and every function throughout your request from the beginning of from the receiving end until it's been left your system.
Yeah. So as you can see, like we discussed in the theory parts of observability, if you have a system like this, now you can answer most of the questions, whether something is slow, whether there are errors. Let's say you have deployed something new. So, you know, if you know the timeline that you deployed something, you know the latencies and the percentiles before that and after that. You can easily compare them and see how it behaves when you introduce a new tiny bit of code and a new function. If you have a span for it, you can see how it behaves, but the latency for it. So all those things can be answered with this by utilizing proper instrumentation and using the correct set of distributed tracing tools. So if you go to this Lightstep's sandbox environment, they have instrumented a lot of like they have a lot of data for those things for over the years. If you
let me check.
Yeah, sandbox. Yeah, in the meantime, I think while Udo is trying to show you some more data or like see how they have maybe try to add a new service. If you guys have any questions, we are happy to answer in the meantime regarding this. I think you have to come from.
Yeah, I think I've logged in with my email.
I think that's fine. I mean,
since I have instrumented it, I think it doesn't show the sandbox anymore.
Okay.
Okay.
Yeah.
Yeah, I think what we got for today.
Yeah.
Do you have anything?
Yeah.
If you guys have any questions, clarifications, we are happy to do it, or we'll share the presentation. You can do some further readings on it. And yeah.
I have a question on Ahiru.
Yeah, okay, go ahead. Yeah.
It's about now. Now, how does it depend on the deployment now? If this set of services are deployed on like ECS cluster or EKS, and how does it differ? So there has to be some sort of agent running on along with the services and push these
It's a great question. Yeah, it's a great question. So, Pood, if you can go back to the presentation and go to the general overview. So, what happens there is, so while planning your deployment of your microservices, there are different patterns that you can deploy your open telemetry or whatever the distributed tracing infrastructure. If you can go to the green box in your slides, in your slides, the green one, not that one, the other one. Yeah, this one. So what happens is you have to so in Kubernetes there are these deployment strategies called sidecars and daemon sets. When you deploy your microservice container, you can either select this agent, the OpenTelemetry agent, as a sidecar or a daemon set, where if it is a daemon set, it will be a per host deployment. If it is a sidecar, it will be running with a particular pod of your deployment. So, for example, if you instrument your application code with OpenTelemetry, and while you are planning your Kubernetes deployment, so the Kubernetes deployment manifest can add another agent pod or a daemon set along with the deployment. So whether it is Azure or Google, while you just need to add another deployment setting to deploy the agent with your microservice. Then the agent, again, you can select a centralized collector container, which is not tied to a container or a pod, where it will run as a standalone collector, where all the agents will communicate and send the collected data to. Then the collector can select where I'm going to send the data into the cloud. So it's another deployment configuration that you need to add with your microservice deployment. So when you have your microservice deployment configurations on that same deployment manifest, you might need to add a OpenTelemetry agent configuration setting. if you have Pubudu a small Docker, you might have the Docker compose file that we used. Maybe you can show it, then he'll get a clear idea.
So it's an additional Docker compose service running the agent.
Yeah, true. Right? That's it. That's basically okay. Yeah. So yeah, as Pubudu is showing here, Docker compose. Yeah. So in this Docker compose, along with your application containers, we can deploy the OpenTelemetry image with whatever the configurations that you are trying to put. The OpenTelemetry config will say where do you want to send it, either zipkin or Jaeger or whatever. So we are happy to share this code base even if you, so for Java you can get a head start, like what are the libraries that you can use and some tricks instrumenting. Plus we'll share you a simple Docker compose as well.
Thanks.
Yeah.
So any questions from others?
Okay, if anyone else don't have any questions, we'll wind it up. I think it was a very informative session today. I believe it's quite useful to everybody. We'll have the recorded session. If anybody missed, you can access it. Thank you, Taridu and Pupudu, for a great session. And we wish everybody Merry Christmas and Happy New Year 2021. Thank you.
Yep.
Thank you. Happy New Year. Bye-bye.
Yeah.